Okay, so let's think about back to the three different interpretations of the derivative. So we saw before that the slope of the tangent line at the function is equal to the instantaneous rate of change of the function at that point and equal to the derivative of the function at c. So f prime of c is equal to each of those things. Let's just see this in terms of, we've looked at the definition of the derivative. Let's think about the slope of the tangent line and the instantaneous rate of the change of this function that we've been working with, f of x equals x squared minus 2x. So above, we found that f prime of 2 is 2 and f prime of negative 1 is negative 4. So f prime of 2, that's the rate of change of the function at x equals 2. And that should be equal to the slope of the tangent line at x equals 2. And so, yeah, that seems believable. So the slope of the tangent line at x equals 2, for every 1 we're going over in x, we're going up 2 in y. So yes, that's a slope of 2 for the tangent line, and that is equal to f prime of 2. And similarly, if we look at f prime of negative 1 equals negative 4, then we look at, here's c equals negative 1, and here's the function at that point. If we try to draw a tangent line to that curve, we see clearly that's negative, and yeah, this is just an estimate, but it looks from our drawing like negative 4 is a good value for that derivative. F prime of negative 1 is negative 4 is equal to the slope of this line. So the line is just sketched. For every 1 we go over in x, we go down 1 in y. So a slope of negative 4. So yes, these are the exact values that we have found using the definition of the derivative. And those exact values give us the slope of the tangent line at the point, the instantaneous rate of the change of the function at the point, how fast is the function changing at that moment in time, and the derivative of the function at that point. So something you might have noticed as we went through that process is that when we found the derivative at x equals 2, it was a very similar process to when we found the derivative for x equals negative 1. So we can generalize this. We can find the derivative as a function of x instead of just the derivative for a particular point. And if we find this derivative as a function, then that function will be valid for any value x equals c. So this is the definition of the derivative function. If f is a differentiable function over an open interval I, that is, for each point c in that interval, the derivative exists, then the function f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h is the derivative of f, and that is a function in and of itself. In terms of notation, there's a lot of equivalent notation. So far we've been using f prime of x, but we can also use y prime, so f of x is y, we can also say y prime. We can also say dy dx, that's the derivative of y with respect to x. We can say df dx, the derivative of f with respect to x. It's also written this way, or dy dx written that way. So these are all different notations for the derivative of f and with respect to the variable x. Depending on context, we'll see different ones of these at different points. So let's consider the example we've been working with, f of x equals x squared minus 2x, and let's find f prime of x as a function as opposed to the derivative at a specific point. So this is, by definition, the limit as h approaches 0 of f of x plus h minus f of x divided by h. And so in our case, that's the limit as h approaches 0 of f of x plus h is x plus h squared minus 2 times x plus h. And then we can subtract off f of x. F of x is simply x squared minus 2x, all divided by h. Now we can work to simplify that. That's the limit as h goes to 0 of x plus h squared is x plus 2xh plus h squared. You can simplify that on the side to verify if you wish. Minus 2 times x plus h minus 2x minus 2h, distributing that negative 2. And then minus x squared minus a negative 2x, so plus 2x, all divided by h. And that's the limit as h goes to 0 of, this was an x squared up there. Now we're just trying to simplify our terms. So we see that we've got an x squared and an x squared. Those terms, a positive x squared and a minus x squared, cancel out with each other. We've got a negative 2x and a positive 2x. Those also cancel out with each other. And so let's see, what do we have remaining? We still have 2xh plus h squared minus 2h, all divided by h. And now we can simplify, or we can factor an h out of the entire numerator. So this is the limit as h goes to 0 of h times 2x plus h minus 2. So we factored an h out of each of the terms in the numerator. And now because we've done that, we can cancel out those h's. And this is equal to the limit as h approaches 0 of 2x plus h minus 2. So we're just plugging in 0 for h. And that's 2x plus 0 minus 2, or 2x minus 2. So this is our derivative function. F prime of x as a function is equal to 2x minus 2. So let's think about the derivative function as a graph in relationship to the original function f of x. So we see the function f of x equals x squared minus 2x graphed above. Let's also graph the function f prime of x that we've just found. So it's the function 2x minus 2. So I'm going to try to stay on the same scale here. So 2x minus 2, that means that at x equals 0, we have a y-intercept of negative 2, and then the slope is positive 2. So for every 1 we go over, we go up 2. So, and it's just a linear function with that slope. So that is the graph of the derivative f prime of x. And we see that this matches with the slopes at different values. So for example, the slope of f of x at x equals 0 should be approximately negative 2. Yes, that works. F prime of 0 should be about negative 2, or should be negative 2, because f prime of 0 is equal to 2 times 0 minus 2, that is negative 2. So the derivative at 0 is negative 2. That means the slope of the tangent line of the initial function at 0 is also negative 2. And f prime of 1 we see, or f prime of 1 we see, is equal to 0. So right here, f prime of 1, the derivative at 1 is equal to 0. And we see that, yes, at 1, the slope is in fact 0. It's a horizontal line, is the slope of the tangent line at x equals 1. And therefore, f prime of 1 is equal to 0. And if we look at some other value, like f prime of 3, we see we're going to have a positive value for that slope. And f prime of 3, if we plug it in, is 2 times 3 minus 2. That's a positive 4. So f prime of 3 is positive 4, and that's also the slope of the tangent line to the original function at the value x equals 3. So let's do one more example together in this video. So I'd like you to try to use the definition of the derivative, that's this right here, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h, to find the function, the derivative function for our function here, f of x equals negative x squared plus 3x minus 1. And so find the derivative as a function, and then after you do that, also find the derivative at certain points, f prime of 0, f prime of 3, and f prime of negative 2. If you happen to have had calculus before, then you know that there is also an easier way to do this. So after we do the derivative the long way using the definition of the derivative, one or two homework assignments. After that, we're going to use the definition of the derivative to prove the derivative rules that you may or may not already know. So as of now, stick with the long way, use this definition of the derivative. Later on, we will be learning shortcuts, but we are going to prove why those shortcuts work. And to prove why those shortcuts work, we need this definition of the derivative. If you haven't had calc before, don't worry about that, but know that we will find a simpler way of doing this later on. But we're going to show mathematically why those rules are valid. So, a little digression there, but I'd like you to now pause and find the derivative of this function using the definition. Okay, so plugging in this function into the definition, we've got the limit as h approaches 0 of f of x plus h. So plugging in x plus h everywhere we see an x in the original function, negative x plus h squared plus 3 times x plus h minus 1 is f of x plus h, and then minus f of x is negative x squared plus 3x minus 1, and that's all divided by h. To continue simplifying, we've got the limit as h approaches 0 of negative x plus h squared, that's x squared plus 2xh plus h squared, plus 3 times x plus h, so plus 3x plus 3h minus 1, and then minus a negative, so plus x squared minus 3x minus a negative 1, so plus 1, all divided by h. And now some things cancel out. So we've got a negative x squared and a positive x squared. We've got a negative 1 and a positive 1. We've got a positive 3x and a negative 3x. So all those things cancel out with one another. And so now we can write simplified limit as h goes to 0 of negative 2xh minus h squared, so distributing that negative that's out front, plus 3h, and that's all, divided by h. And so now we can factor an h out of every term in the numerator. Limit as h goes to 0 of h times negative 2x minus h plus 3 divided by h. And now we can cancel out those h's. And so we've got the limit as h goes to 0 of negative 2x minus h plus 3. And that's equal to, just plugging in h equals 0, negative 2x plus 3. And that is f prime of x, the derivative function for our function, which was negative x squared plus 3x minus 1. One thing you may have noticed as a pattern is that we can, for all these examples, we can factor an h out of the numerator, and that allows us to cancel the h in the denominator. So the definition of the derivative has always got an h going to 0 in the denominator. And so if the derivative of a function exists, algebraically there's always going to be some way that this works out, some way that we can somehow get rid of the h in the denominator. Because if we couldn't, then the limit would not exist. So anytime that a function is differentiable, and not all functions are differentiable, we'll see examples of functions that are not, but anytime a function is differentiable, we'll somehow algebraically be able to factor h's out and do things to get rid of any h's going to 0 in denominators. Okay, so we were then asked to find the derivatives at specific points, f prime of 0, f prime of negative 2, and f prime of 3. And so this is just plugging in 0 into the formula for the derivative that we found. 2 times 0 plus 3 is 3. F prime of negative 2 is negative 2 times negative 2 plus 3, so that's positive 4 plus 3, that's 7. And f prime of 3 is negative 2 times 3 plus 3, so that's negative 6 plus 3 is a negative 3. So those are the derivatives of that function at those specific values for c. So let's again compare the function of the derivative with the original function itself. So our original function is graphed here, negative x squared plus 3x minus 1. That's that parabola pointing downwards. And then we just found our derivative, f prime of x is negative 2x plus 3. So again, this happens to be a linear function. Not all derivatives will be. If we think about graphing this function alongside the original function, so I'm going to try to keep about the same scale. Then we've got f prime of 0 is 3, we already know, is the y-intercept, just plugging in f prime of 0. And f prime of 3 is negative 3, 1, 2, 3. And we know this is just a linear function with a slope of negative 2. So we've got a slope of negative 2 for that linear function. And we can see that at any point, the output of f prime of x, matches the slope of f of x. So here, for example, the output at f prime of 0 is positive 3. That should match with the slope at x equals 0. So here's x equals 0. What's the slope of that function? Yeah, it makes sense that that's about approximately 3. If we look at, well, let's look at this point here. This is x equals 1.5. Should be right there. So at x equals 1.5, we've got a slope of 0. F prime of 1.5 is negative 2 times 1.5 plus 3. That's 0. That's the slope of the tangent line to the curve of the original function, and that's also the output of the derivative function. At x equals 3, we saw the output was negative 3. At x equals 3,